Well, good morning, everyone. I hope everyone had a nice weekend. Before we get started on the lecture for today, I just want to remind everyone that the next exam is going to be on Friday. Just like the other exams, I'll actually open it up at 12:01 on Thursday morning, and it'll be available until I think it's 1 p.m. on Saturday. So there'll be 3 days, to basically to take the exam. You can take it at your leisure, same exact format and everything as last time. To facilitate everyone doing well in the exam, or at least that's my intent, I will do an exam review at the beginning of class on Wednesday. I'll post that probably online tonight or tomorrow. But just like last time, there'll be an exam review posted uh, and an exam review during class that'll be available for all of you to look at. In terms of material, the exam's only going to include material up to and including last lecture. So basically, where we're going to end is talking about metal contamination for mining, but it will up to include some aspects of water quality. Obviously, based as you probably recognized, I usually focus it so it's not too heavily weighted towards the materials that we have, just finished recovering. So that's the update of the exam. Again, nominally Friday, although Thursday through Saturday is your window. Don't expect it to be hard, exact same format and whatnot. Um, as we get closer towards the end of the semester, I know a lot of you are going to be traveling, leaving campus, and all those different things. I just wanted to make sure you're aware that all the lecture notes, so the files, are up from now until the rest of the semester. Everything we're going to cover through the end of the year is now online and available in PowerPoints. I will keep doing recorded lectures, either synchronously or posted them the night before, like we've been doing. Um, but basically all the files are there, which leads me to my next point, which is that the final two remaining worksheets are also now available online. So the worksheet 11 isn't due until next week. There's nothing actually due this week except for the exam. So worksheet 11 is due the following week, and worksheet 12 is due the week after that. It's actually due the last day of class, I believe. But the reason I bring this up is that they're both open and available now. If you want to work ahead looking at the PowerPoints, you can feel free to do so and have those sort of out of the way if you're going to have a busy end of your semester here. I want to make it as easy as possible as we transition into the end of the year. And then the last topic I wanted to bring up, just to alleviate stress, is that December 8th is the date for our fourth exam. It'll be heavily weighted towards the material we're covering this week and the remaining 3 weeks of the course. But some of the materials that I'll cover in the exam review will be available. Will be fair game. I'll have an exam review online for you. I'll just record it ahead of time over Thanksgiving. So you'll have it for almost 2 weeks before the final exam. And just like the exams during class, I've set it up so the final exam will be flexible from it's a nominal due date is December 8th. It'll be flexible from December 6th through December 9th, only one day after the deadline because of having to get grades in on time. So there'll be an exam review for the last one. It'll be the same format, all the same stuff. I won't go belabor that point at any greater depth, but it'll all be available to you by Thanksgiving. And then what I'm also going to do is that once we leave for Thanksgiving, I'm gonna tape all the lectures ahead of time, so that by the time everyone leaves campus for Thanksgiving, or if you're off campus already, that's totally fine. Everyone will have all the materials, including reviews, lectures, and whatnot, before by the Wednesday of Thanksgiving. So everything is available to you to read at your leisure. The only thing you'll be forced to engage with the course between the 6th and the 9th in order to complete the final exam, but I don't anticipate any problems with that. You'll have ultimate flexibility. So any questions with that, feel free to send me an email. I'll talk about that, I'm sure, during the exam review, and I'll send an announcement describing all that. But I want to make sure everyone knows that, we're going to have basically from now until next Wednesday of live lectures. All at that point, Wednesday, we'll have all the remaining lectures taped online rather than synchronous, so they're available at your flexibility. And we'll have a lot of flexibility through many exams. Worksheets, again, are already available for your enjoyment throughout the rest of the semester. So many of you will probably have the vast majority of your grade, in the books, and a pretty good idea what you're getting down the home stretch, which hopefully many of you will do very well. Okay, so back to the actual lecture material. What I'm going to finish up with today is water quality issues. We ended by talking about metal contamination from mines, particularly from the Berkeley pit as an example of a abandoned mine filling it with water and the metal contamination causing major deaths of snow geese and whatnot as recently as 2016. What we're going to move on to now is actually not talking about something that humans have done to lead to, mass poisoning, but talk about something where, sort of the punchline, I don't mean to be glib about this, where Mother Nature is effectively getting away with murder. And that's actually using an example of a case study in Bangladesh and West Bengal. In that area, basically, you have, you're in a deltaic plain with the Himalaya mountains to the north. The Himalayas are rapidly undergoing orogenesis or mountain building. They're being eroded, and as that's occurring, you're seeing erosion of igneous metamorphic rocks and sedimentary rocks that are getting exposed by the uplift in the Himalayas. And as a result of that, the vast majority of southern India, Pakistan, and Bangladesh are actually covered by alluvial sediments freshly deposited in the last few millions of years, and you're in a major deltaic plain. So, effectively, the story here is a bit convoluted, and I said Mother Nature is the one getting away with the contamination, but in reality, it's a lot of decisions, made with the good intentions. That's a classic case of the road to hell being paved with good intentions that led to some really major environmental problems, in the area. So the story starts prior to the 1970s. Bangladesh, in particular, had one of the highest infant mortality rates in the world. There are a variety of health maladies across the entire alluvial plain of that area, including Pakistan, India, and Bangladesh. And most of the discussion at the time was trying to improve water, sanitation, hygiene access. There's ineffective purification, sewage systems, materials for sewage weren't being, pushed out of the water supplies very effectively. Purification, because of the organic richness and levels of contamination and population intensities, were really not possible. So at the time, UNICEF and the World Bank, again, road to help pave with good intentions, proposed that what we really needed to do in that area is stop using surface water, stop using shallow hand-dug wells, and actually install deep wells that tap into the groundwater. And literally at that time, millions of wells were constructed to go to a deeper aquifer that would be protected from the shallow surface contamination of sewage, agricultural runoff and things like that. And the great news is that the infant mortality rate in diarrheal disease is reduced by 50%. So it's a major public health victory, or so we thought at the time. What was the unintended consequence is that actually drilling into that deeper aquifer, accessing the water that was in the subsurface, actually led to the contamination of more than 2 million drinking water wells, and the contamination of an estimated, the estimates range from 20 to 50 million people, across that entire area. But 2 million wells in particular in Bangladesh that are contaminated with arsenic above the local government drinking water standards, as well as the arsenic standards for the US EPA or the World Health Organization. So, the British Geological Survey was actually the folks who were helping install these wells. They found that in Bangladesh alone, 28 to 35 million people have been exposed to arsenic contamination, with concentrations between, well above the drinking water limit, and that basically, another group of people, quite a large group of people, dozens of millions, were contaminated above what was expected to be safe, not just the local concentration levels. So how did this actually happen? Well, what people ended up realizing is that there was a lot of ideas. People thought it was, the wells are poisoned by people. There was surface contamination, maybe even agricultural runoff from rice paddies is causing arsenic to leach into the groundwater. And effectively, it actually goes back to some of the processes we talked about earlier this semester, where instead of that was actually geology that led to metamorphic and igneous rocks being eroded from the mountain belt, the Himalayas. Those sediments are getting deposited out here, and once they're deposited and they're buried deeply enough in the right pH and EH conditions, the arsenic is actually being mobilized by microbial activity in these aquifers. In many cases, it led to severe arsenic poisoning. Here's some lesions and discoloration of the skin that often in the hands and the feet get this. For background, arsenic is the 20th most abundant element in the earth. There's some minor things where it has some biological benefit at very low concentrations, but at modest to high concentrations, it's exceedingly toxic. And basically what was identified is that the sort of alluvial sediments, which became lithified in many areas and are actually just alluvial sediments in others, contain high arsenic concentrations. So near the top of the aquifer, the same arsenic levels are present, but it was in oxygen-rich conditions. There was fresh water percolating down through, high in oxygen and moderate pH. And in those conditions, the arsenic stays tightly bound to the mineral phases. As the water percolated deeper, and microbes, respiring bacteria, consumed all the oxygen, and the oxygen conditions were decreased, reducing conditions in the aquifer, arsenic was pretty readily released and led to this contamination. There's a whole variety of health maladies, including cancers, neurological deficits, cardiovascular health issues that are related to this. But basically, the punchline here is that the intention to go to drill deeper wells, prevent one form of very certain mortality and morbidity related to infant health issues and chronic diarrhea, actually led to a different set of health problems. This is not an uncommon theme in many parts of environmental science, is that people don't intentionally do stupid things, right? People don't intentionally drink contaminated water. They usually do it out of necessity. In many cases, going to another source, we find there's challenges with that. So, what are the possibilities to sort of improve upon this? That's sort of the question. You have, nominally 1 billion people living in an alluvial delta in this area, drinking water that has a pretty high probability, particularly in areas where the groundwater is flowing long enough to have microbes present and reducing the oxygen levels, have almost a certain probability of arsenic poisoning, particularly as you get close to the Bay of Bengal. So, in the reality, what's been done, if you talk about solutions, how are we going to fix this problem? It's a tough one. One of the ways that's been done is actually to use, to try to install filtration systems. It's expensive. It's has a lot of infrastructural costs, has a lot of ongoing maintenance costs. As a result, it's not been particularly effective. Another strategy, people try to use low-cost methods. Often, and this doesn't work on a global scale, but one of the things people have proposed is actually squeezing lemons and putting lemons into the water, changing the acidity and allowing the arsenic to become absorbed onto solids, and that can be low-cost treatment systems. The reality is there's not a very effective way to treat it. Instead, what people have done is try to drill much deeper water wells down below the arsenic and get into deeper bedrock units that have already lost the arsenic by millions of years of weathering. So part of the process here, as I should have said, is that it's not just reducing conditions. In those reducing low oxygen conditions, the arsenic is mobilized, and over enough time, that arsenic can be stripped out by further episodes of fluid migration, groundwater migration. And as a result, people have tried to drill deeper, go to areas that were exposed to flowing water for long periods of time, and they've identified lower arsenic levels. The challenge is, if you remember back, we're talking about multiple millions of wells, all drilled at a cost. So let's just say the average well like that might cost about $20,000. You're talking about billions of dollars of wells to repeat the process. And when we recognize that the cost of drilling increases per foot of depth, you're talking about many billions and billions and billions, dozens of billions of dollars to actually get enough water wells below those levels. So, when I made the comment earlier in this lecture set about the fact that there were, billions of people who suffer from lack of water quality, nominally 2 billion of them are just affected by the Himalayas themselves, where this process occurs through Vietnam, Cambodia, Thailand, right around to India, all the areas where these sediments are being freshly deposited and wells are sunk to relatively shallow levels. This is at risk. So I've worked on this, a lot in India and Bangladesh as well as Vietnam, and it's a challenge that doesn't have a very simple, cost-effective solution. One of the things that this is sort of a survey of different environmental contamination. This is one where it really wasn't clear if it was humans or Mother Nature causing the problem. So switching gears from the arsenic in Bangladesh, I'm going to talk a little bit about methane contamination resulting from hydraulic fracturing in the United States. As many of you might have heard, there's the advent of horizontal drilling hydraulic fractions. We'll talk about more in the next series of lectures. It was a major development and major technological advancement in petroleum geosciences and petroleum engineering in the last 10 to 15 years. And the concept is you drill wells down, you can directionally drill laterally into a shale formation, contact the maximum amount of the source rock. Then you can do what's called hydraulic stimulation or fracking, which is put pressurized water and other fluids in it at high enough pressures to fracture the rock, release the target methane and natural gas and oil out of the rocks. And that was and has been an incredible success for the petroleum industry. We now, are producing oil and gas from formations that we've known about for generations but couldn't do anything about. Now the United States, who was setting up to be a net importer of methane in about 2005, has itself about 3,000 years of methane supplies at current use, and enough methane to expand natural gas usage to eliminate coal and other resources and burn methane. We'll talk about the fossil fuel aspect of that later. But the sort of sticky problem with it was the fact that where this drilling was occurring, people kept observing bubbling methane in their water wells. So people were observing methane, coming out of it sort of shakes and pulses out of their water. They turn their water on, their well would actually start to share, their pipes would actually start to shake, and they started to recognize some odd odors of sulfur odors. And then eventually people started to see if it was gas and throw it on fire. And in many cases, they actually were able to do that. So, the topic kind of went back to the early parts of petroleum development, where this often occurs very intensely in certain areas. There's some environmental contamination issues. And the question was really, was this something that was natural, or was it actually caused by the hydraulic fracturing process? For the background, one of the ways we look for oil and gas historically is by looking for seeps of methane and oil in other areas. So many argued that this is just, we've known methane's been methane's in them hills because of the fact that that's how we looked for oil and gas there originally. Others said, wait a second, there's been drilling and activity that's released this methane. That's why contamination is present. Don't worry, I won't make you interpret these graphs, but the punchline, this is all for work I did over the last few years, is that what we observed is that where methane occurred naturally, it had a very distinct chemical characteristics. It was migrated with salts and methane, and in many cases, there were subsets where activities near drilling appeared to release methane. So I won't make you go in. Don't worry about this in any detail. The punchline is the reality is the answer is both. There is a natural amount of methane all over petroleum basins, not just in Ohio and Pennsylvania, but all over the world. The idea that methane leaks out and that's how we find oil and gas reservoirs is an important one. But there's also a small subset, probably about 6% of wells, natural gas wells actually have leaks, and some of that 6% have methane that leaks to the surface, which is released to the atmosphere and/or contaminates groundwater. If you think that's a controversial number, some environmentalists think my numbers were too low. That could be higher. Some oil and gas companies think they're too high. That it should be. They do a much better job. But for perspective, Schlumberger's own marketing materials to oil and gas companies suggest that about 15 to 20% have problems. We only identified about 4 to 6% of wells. But to give you a general sense, and we'll talk about this more in the next lecture, is that what people were doing is trying to drill down into shales to frack and hydraulically stimulate wells. But what happens is that in most normal natural subsurface systems, there's source rocks that can generate oil and gas. That oil and gas is buoyant, it's lighter than water. It migrates up until it hits a rock that can't migrate through, and it accumulates in certain areas. These are called conventional reservoirs. Basically, this is what we used to try to drill a well and tap in and sort of suck this out like the soda out of a between the ice and a Coke cup or something like that. And oftentimes the pathway to get there, you drill through these things, and people were releasing methane, more likely from these overlying formations than fracking itself. So to give you a perspective, a lot of this activity just comes down to the fact that we can't engineer things perfectly in the subsurface. Think about the scale of this. We're trying to drill something a mile deep. We don't take a right turn, but basically curve the drilling borehole and go up to a mile or a mile plus long and keep everything perfectly concentric. And as you can see here, by a well that was cut, it's very hard to do. Oftentimes the boreholes aren't perfectly aligned; they deviate. But the more important thing that leads to a lot of these problems, you see here, is this is actually the area around the borehole is called the well annulus. So, this particular steel casing is designed to keep the water safe, and companies are well intended when they do this. And this spacing between there and outside production casing, in this case, or on the outside of the rock wall, is actually called an annulus. And what happens is that annulus is filled with cement. But if you notice here, in that cement, when cement solidifies, it contracts. Those contractions actually make fractures and little pathways where gas can migrate through which we believe is what caused most of the rest of the contamination issues around the area. So as a result, I won't bore you too much with geology, but these natural conventional accumulations occur in many oil and gas basins, such as the areas near the Himalayas or in Western Canada. You can kind of find topographical highs like these are called the anticlines. You can drill a well and you can produce oil and gas. But where we live here, if you're in Ohio or in the Appalachian Basin, we're in a very old petroleum systems basin where these anticlines have actually been eroded away. In fact, these anticlines are particularly easily eroded over time, and they actually end up being little valleys. And a lot of these, in most cases where we found the naturally occurring methane, it resided in these valleys that were actually eroded away by the eroded cores of anticlines, allowing these conventional oil and gas traps to be very close to the surface and accounting for the elevated levels of methane and salinity in those areas. So I suppose the lesson here, at least with this one, it's true of all different types of contamination, is that you have to think of geology. We talked about the processes that form them very early in the semester, but in reality, after it's formed, most of the rest of the history of a basin is being eroded, and as a result uplifted, and oftentimes deeply residing geological features, including natural gas, get to be really close to the surface and can cause some natural contamination. And in many cases, when we're drilling a well, through it, we can release methane that causes a lot of problems. So, broadly speaking here, not talking about any particular contamination, the way this works particularly in the U.S. and globally, it's largely done by the World Health Organization, although many states and the European Union, for example, have their own guidelines. Is that independent of the contaminant or independent of the parameter that reduces water quality, the U.S. Environmental Protection Agency has established, minimal drinking water standards for a range of chemicals and other compounds. For an example of this, the guidelines for lead is basically reduced the threshold, so lead can no longer be used in water systems for human consumption. Of course, as you saw in Flint, Michigan, or as you see in many urban areas around the country, is that these lead pipes aren't necessarily removed. There are many of our early cities, such as Boston and Detroit, Philadelphia, where the lead pipes are still present, and if you don't have the economic wherewithal to remove them, you have often a very discreetly biased case where the most impoverished portions of the population are living in areas where the lead pipes are still there that can be leached out. Obviously something like lead, as you know, has many toxic aspects to the nervous system, kidneys. Is particularly hazardous to infants and pregnant women. But most of the contaminants, using lead as an example here, are all managed by EPA guidelines. So we won't go through these in great detail, but this gives you an example of what this looks like. Most of them will have a maximum contaminant level. If the levels in a given well are above that, measured by a certified lab, the EPA or the local state authorities can actually what's called red tag the well, basically declare it not fit for drinking. And then beyond that, the well either has to be shut down or it can be evaluated whether if something is just a little bit high for arsenic for drinking water, it might still be possible to use for agriculture or some other purpose, or gray water usage or something like that. So just to recap the water quality discussion, water pollution is the degradation of water quality by humans. Contamination is just diminished quality, period. Could be natural or caused by humans. Remember, pollutants can take many forms, degrading organic material, nutrients and fertilizers, synthetic chemicals such as organics produced by humans, heavy metals released by industrial activities such as acid mine drainage or smelting, as opposed to something like arsenic that's released naturally. And then, of course, oil and natural gas is both a resource but also a contaminant in many situations. And I think the punchline I should have made earlier with the discussion around the fracking in the Appalachian Basin in particular is that what it highlights is that many people living in rural communities actually have access to really poor water quality, independent of whether it's natural or contamination. But clearly, if it's caused by humans, somebody should be responsible for cleaning it up. Other points here is that point source pollution comes from a location, industrial outflow pipe or sewage outflow pipe, while non-point sources often come from diffuse areas such as agricultural runoff or sometimes even methane release across areas. One of the key metrics people often go to, which actually controls a lot of the contamination related aspects, is biochemical oxygen demand. The level of oxygen or the low levels of oxygen in an aquifer in particular, or surface water is a really common measure of the amount of organic content, but also is really important for predicting how mobile certain things like metals and whatnot are going to be. As we mentioned, it's not really possible to test for everything. So things like biochemical oxygen demand, fecal coliform are usually used to look at levels of bacteria. They don't necessarily, cause problems themselves, but just like I mentioned with BOD, it can help you understand whether metals can be released or other things like that. Fecal coliform is often used not because itself is toxic, but because it can inform you about potential for other bacterial pollution of water, let you know if it's just not worth it to drink it or if it needs to be tested for other things. And then obviously, talking about things like the Great Lakes, just to highlight here, in our region, eutrophication, caused by nitrate and phosphorus inputs from agricultural practices actually leads to major decreases in major increases in biochemical oxygen demand, major decreases in oxygen levels, and can cause things like fish kills and reduce water quality in many ways. So that's an aspect that's important in our region in particular, and will continue to be so for a long time. So where I'm going to go on to next here is actually transitioning from water quality over to talking about energy. Particularly what we're going to talk about initially is fossil fuels. And towards the end of the fossil fuel energy discussion, we'll talk about some of the potential solutions on the horizon. But it's useful to have the perspective of fossil fuels. I'd love to tell you that the world's about to turn green. We're going to have everything done by solar and wind, but the reality is majority of our country's energy, about 90% still comes from various types of fossil fuels. We'll talk about some non-fossil fuels later on, but I want to give you some background of this so you understand what we're talking about. So we're gonna first talk about the general patterns of energy consumption in the United States. It's useful to have some knowledge about what we're using and how we're using it. Going to focus on the types of major fossil fuels, how they're actually extracted, where they form, and some of the environmental impacts associated with developing fossil fuels. And then basically some of the controversies surrounding fossil fuels in the U.S. in particular. What's useful way to start thinking about energy is just thinking about the massive amounts of it that we use and the perspective about where we're actually getting that energy from. So this is a map actually shows you, and for some reason on my computer in really poor quality, I'll try to get that fixed, but it's not terribly important. This basically looks from the 1950s up until and including projected from to 2020. And basically what this shows you is electricity generation by the type. So notice here, natural gas, this is in year 2000. Natural gas has come on as an increasing component of the energy production. You've seen that as a result of hydraulic fracturing, the availability of natural gas. People are converting coal-fired power plants to natural gas power plants in order to develop electricity. The idea being here is that coal's major advantage, by the way, is that it can be stored in a parking lot or a field and put on the fire whenever you need to generate power. So it can be on-demand power supplies. Most of the rest of the energy resources, sun shines during the day, wind blows when it blows, and as a result, you have to have some component of energy storage to use those other sources. The advantage of coal and now natural gas is you can sort of light them and generate power whenever you want to. So for a long time, as you can see here, up in the mid 2000s, coal was the largest generator of electricity. It still is, but you'll notice this percentage has actually dropped down. Where coal's being removed as an energy provider at the expense of natural gas coming in. From the perspective of purely CO2 emissions, you can note that the sum total of the percentage derived by either oil, natural gas, and or coal is not actually decreasing much at all. In fact, it's remained about the same. There's been trade-offs in coal and natural gas, but the projection is, I think, by about 2030, the last time I looked, natural gas will exceed coal. Many people think that's going to be sooner, and in light of a renewable energy resource coming in, that's one of those is possibly going to be the majority of the energy production, electricity production in the U.S. Beyond that, the next big chunk of energy actually comes from nuclear. You'll note that the nuclear looks about constant, but actually this is something that's not increasing at all. We can point to problems with things like Fukushima in Japan, within the last decade. But the reality is that in the United States, 3 nuclear power plants, I think, have went offline in the last 2 years. No new ones have been built since the 3 Mile Island, episode in the 1979. and as a result, you're going to see nuclear power continue to decrease. So that's a non-fossil fuel energy source. Of course, has its own environmental risks that people are concerned about. We talked about waste storage last time, but by and large, that is basically moving away. The next most important form of electricity generation is hydroelectric power, and above them you'll see wind, wood, a little bit of petroleum, which is not particularly big in the U.S. this time. Geothermal and solar you can barely even see on this image. It's not just the poor image quality. So we'll talk about this more as we go on, but the good news is we're seeing more solar and wind. The bad news is that's actually come at the expense of largely hydroelectric power being diminished, and geothermal energy also being diminished. The issue with the hydroelectric power is, as we talked about earlier in the semester, is the removal of the dams that generate hydroelectric power to try to restore the ecosystems for fisheries and other components. So it's a trade-off. We talked about this earlier in the semester. China's building them to generate hydroelectric power that's non-fossil based. We're removing them to try to restore the ecosystem. I'm not putting a value statement on either one. I'm just stating that's what's happening. So, for perspective, by 2015, we produced about nominally 100 quadrillion BTUs of energy. That's an incredible sum of energy. We are now the second largest producer of energy in the world. China has surpassed us. India will surpass us in not very long. But the updated perspectives. This is the energy consumption by energy consumption by various energy sources. We've now moved into, even though most of the power generation is still by coal, where for other purposes, industrial activities, even some mobility, transportation, we package these together in petroleum, natural gas. So the oil industry, if you will, nominally accounts for about 75% of our total, or 65% of our total production, energy consumption, I should say. Coal, largely for electricity generation, is only 16%. Nuclear power, although it's decreasing, around 9%. And the total package of all the renewables in the U.S. is about 10% of the energy production. I won't test you on many of these numbers. Don't worry about that. I have some examples of key numbers in the worksheets, but the numbers aren't as important. It's just getting a concept here that power generation, dominantly coal, natural gas, total energy consumption across industry, mobility, and power generation. It's basically most of the pie comes from oil, natural gas, and coal. So fossil fuels. That's why we're spending so much time on this. We'll talk about this as we go on, but the renewable slice is changing a lot in the last decade. It used to be that 10% of this piece of the pie was hydroelectric. The next 20+% was actually wood. Biofuels made about 22%, and then biomass burning, bio waste, burning dried, sewage cakes. And in many parts of the world, it's dried cow pies. Was a big one. Geothermal, solar, and wind made up the rest of it. Over the last, less than 10 years, solar in particular has made a big move forward. The price points come down, and people, can understand the value of that. The challenge with that solar energy generation is twofold. One is that you have to, it is true to say that solar is only generated during daylight hours, and as a result, the first challenge is actually finding energy storage capacity. How are you going to generate make the right type of batteries, or otherwise store the energy to basically be used on demand? So there are many facilities trying to generate batteries, some trying to take the energy that's generated and do some sort of electrolysis of water, generate things like hydrogen. Others are simply doing things like taking water and pumping it uphill during the day, letting other sources of energy be used for power consumption, and letting the water flow back down past a turbine to generate energy during the nighttime hours. So put out a big solar field, maybe half of it puts water up the hill and half of it generates power that's used. The water can be put back down, can flow back down and generate power. So the punchlines here is hydroelectric power are decreasing, biofuels are actually decreasing, solar is increasing, and winds remain about the same. But the bad news, I would say, from our perspective of getting off of fossil fuels, that the percentage of power generation from 2010 to 2015, 2020 by renewable energy resources is about 10%, and that hasn't really changed very much. So we haven't moved much away from coal or gas. We have, as a country, as we'll talk about in a minute, improved because we're burning more natural gas than coal. which reduces carbon dioxide emissions, for example. So, in perspective, this just compares 2017 to 2018. Coal continues to decline. Natural gas continues to increase. Nuclear, more or less, actually stays the same. And it doesn't look very different compared to these others on the graph, but it sort of waffles around about the same. Hydroelectric power, this only captures 2 years of comparison, but it's continued to decrease. Non-hydro renewables have increased, but that's basically balancing out what's lost from water. And then one of the things that's changed a lot, if I go back a few slides here, you can see that petroleum used to actually make a much bigger portion back in the in the 80s, 70s, 80s, and 90s. We've now improved refining processes to the point where we no longer are using valuable things like petroleum for energy, just for combustion. We usually refine other products. Some of them could be gasoline used for combustion, but many other products are made, such as plastics and various things with that. So a big trend, I should say, along with natural gas usage for electricity generation is that very relevant to places like Ohio is that most of the uses of oil that I just alluded to, if you're refining the oil down to make gasoline, to make material, feedstocks for plastics, things like that, a big trend in the petroleum industry is actually to take things like methane and ethane, particularly ethane and propane and sort of low molecular weight hydrocarbon gases, and actually rather than tear oil down to the right size by refining and catalysis, we're actually now combining low molecular weight molecules like ethane and making feedstocks to make plastic. So, right now, I think it's something like 95% of the plastics in the world are manufactured in China. I don't know, hold me that number. I think it's about right. And, if you heard about the Tri-State Energy Partnership, Pennsylvania, West Virginia, and Ohio, with all the natural gas in our area, are building 3 large ethane cracker plants to actually make plastics manufacturing in this area by assembling the feedstock molecules from low molecular weight hydrocarbons. So, one of the things I wanted to highlight here, and this is one of the fundamental problems. People say, well, we should just stop burning fossil fuels. Well, there's some challenges you have to be aware of. The reality is that if you look at the capacity to generate electricity from a variety of sources, our total capacity is really doesn't go above 10% for nuclear. Coal can go up to about 30% of our total capacity. Natural gas has the capacity to be much more greatly used, up to 40%. And in reality, our hydroelectric, other renewables, make up nominally 13%. The reality is there are certain processes in how you actually generate power that are very heavily influenced by the process. For example, nuclear power creates a base load of power. You can't really ramp it up and you can't really slow it down very easily. As a result, independent of what other types of energy, electricity generation is on the market, the nuclear plants basically have to stay on and keep producing. And as a result, importantly, this is capacity. This is how much electricity is actually generated. Even though the total capacity in the United States is only about 10%, almost 20% of the power comes from nuclear because that base load stays on at all times. And those are, built in fixed long-term contracts, using a non-fossil energy source, and we're going to maximize energy production out of them. So if you notice, nuclear is being overused compared to its capacity. Nothing wrong with that. That's just saying that, no matter what happens every day, the nuclear power is being output at certain levels. The other aspect here is that you notice coal is actually much larger in terms of its actual percentage of use than its capacity. Natural gas is much lower. So this number is probably going to change in the next decade. But the question you want to ask yourself is why is this the case? Why is it that coal only has the capacity to generate about 1/3 of the power, but we generate almost half the power in our country from this purpose? And the reality is that the nuclear load is always on, generating power. And what happens is something like a hydroelectric plant, you can't easily just turn it on at, if everybody's coming home in the winter, heating their house on electric, not everyone has electric furnaces, but electric heating at, 5 p.m. to 8 p.m. It's not easy to sort of ramp up nuclear or ramp up natural gas, or certainly not easy to ramp up renewables at that time, where coal can be put on and burned. And then you can let it, over a few hours, power can be generated and it can be removed. And one of the fundamental problems that lead to this, on-demand energy production is the fact that electrons or electricity is to my knowledge, the only commodity in the world that has to be consumed exactly as it's produced. We can think about a future that involves storage, or we're storing that energy someplace and letting it be used in batteries. But on a realistic basis, the vast majority, 99.999% right now, has to be consumed exactly as it's produced. So you have to produce it exactly when you're going to have it be, when the users are wanting it. As a result, coal is can be burned really quickly on demand, and then it burns fast and burns hot, so it can basically produce electricity exactly as it's needed. As a result, there's going to be transition to more and more of that by natural gas, but the high BTU load and the immediacy of that coal burning is why it's so disproportionately used. There is a push to make sure that renewable mandates, there are mandates for renewable things like hydroelectric and other things, so that as they're on the market, they have to be used just like nuclear to sort of mitigate some fossil fuel usage. And that's an area you're going to see, I think, active development in the next few years. So, in perspective, looking at the same data a different way, something that the numbers look clear. I apologize again for that. Coal's decreasing, natural gas is coming up. There's some changes in the renewables, but you can pretty much, as I've reiterated multiple times now, you pretty much expect that those are going to remain about the same. Although there's a lot of optimism if we can solve the storage issue, or we can find some other way to use the electrons to our benefit to offset other activities during daytime hours. You'll see more and more solar. The price is coming down. It's an emerging technology. It's got a lot of capacity, but the problem is that the actual loads aren't extremely high, and the demand is not really directly matched with usage, which goes back to the problem of you have to buy it as you generate it. So there's a future there, but it's still a lot of engineering and policy has to be worked out to make it happen. So I think I'll move forward, but these are projections based on those aspects, and effectively, the punchlines are that coal and natural gas still make up the vast majority, although coal is declining and natural gas is increasing. Where that becomes important, quite frankly, is looking at this in terms of how we're gonna plan for the future, how we're gonna try to use this energy to line up industrial activities with daytime usage so we can maximize that percentage. The optimism of all these changes, particularly reducing coal combustion, is the fact that in about 2000, 2005, electricity generation and carbon dioxide emissions in the United States were actually increasing. This is right in the middle of the battles over the Kyoto Protocol. This even before the political battles over the Kyoto Protocol and the Paris Climate Accords, both of which were designed to set standards or thresholds on how much CO2 to be released, and in fact reduce the carbon dioxide emissions. I'm not taking a political side on this, but it's interesting to note that actually we very controversially did not participate in either the Kyoto Protocol or the Paris Climate Accords. But the relatively good news, independent of that, whatever your viewpoints on that are, is that CO2 emissions, and especially CO2 emissions per capita in the United States, which were projected to continue to climb, continuously, have actually declined quite substantially over the last 15 years or so. So there's the good news and the bad news here. The good news is our emissions in CO2 have actually decreased. America is no longer the highest CO2 emitter in the world. China and India both surpassed us in that regard. Both of them seeing rapid development of their economies and infrastructure. The bad news is, if you look at most of this decline, it was actually staying about flat. That's probably about what improved engineering and technology utilization got us. And most of that decline has actually been post 2008. After the last economic crisis, where we saw manufacturing, decrease, and in fact, economic output, by and large, actually decreased over that time. So there is still, unfortunately, a balance between CO2 emissions and the economy. If you recognize that our population is about a third of China's per capita, we're still right there with them in CO2 emissions. But there is some reason for optimism: increased efficiency, increased usage of renewable resources, less utilization of coal. So largely, most of this benefit has been attributed to a combination of slightly declining per capita GDP, but mainly to reduction of coal and advent of more natural gas development. Before we move off of this, just really briefly, just want to make sure I was where I was at. Before we move off of this, one of the things that's projected to see this improve is actually the utilization of decarbonizing fuel sources. So there's a lot of discussion. You probably saw some of this if you watched some of the election discussions. There's still a drive to move towards more solar, more wind. Again, that issue largely comes down to you know energy storage. How do we store or utilize the energy when the sun shines, the wind blows? Um, Americans are not the most patient people. Electric cars sales have increased a lot, but there's still a big lag time in how long it takes to recharge those batteries, and people, to first order sort of struggle with that, I think, still. Um, but one of the goals here is actually, develop things that fuels and use for mobility. So one of the examples has been more utilization of hydrogen. It still can be liquefied or used as a gas phase. It can be used for transportation. Not everything goes like the Hindenburg, which actually did eventually burn hydrogen, wasn't actually started by that. There's other efforts to improve battery storage to actually, create batteries that can store more energy, allow electric cars to drive a longer time, or reduce the amount of energy required to move them by making lighter vehicles, things like that. The reality, I will tell you from my perspective, I think the battery storage issue is a really big challenge. It's an intellectually challenging thing to even kind of conceive of properly, because if you were to think about why we actually use coal, it's because it can do what we want when we want it. If you think about why we use gasoline for transportation, it's because you can put it in your car and you can drive off and it goes with you, and it's light, it's energy dense, and it's a perfect fuel for getting around. People don't use gasoline because it's evil. They use it because it works. All right. So I'm quite optimistic about the future, where things like hydrogen can play a role as a carbon neutral or even a carbon negative fuel source, because it can be used and transferred, can be moved with you. 10 years ago, a big push was involved with biodiesel and biofuels. Most folks have now recognized the price point just doesn't get to be economically competitive, and people kind of went away from them largely. When it comes to the batteries, I'm a little bit more pessimistic, because you're always talking about, as we've alluded to several times, we'll talk about in our last set of lectures in this course, is that you always come down to precious resources. Making batteries require large volumes of special precious metals and things like that, and as a result, there's a big wave of mining and processing that has to be involved in them. So I'm still not optimistic that we can get to the point where many of those resources can be harvested without actually having a big carbon footprint to get them. And more importantly, and I'm not against electric cars at all. I think they're fantastic, and I'm really excited that they have the potential to go forward. But look at something, one of these graphs. If you're powering an electric car in the United States, no matter how careful you want to be, if you're using the grid, I mean, you can develop your own solar panels if you're wealthy enough, but by and large, you're still getting electricity that is derived from largely fossil fuels. And most importantly, as that electricity is transferred through the power lines, there's an inefficiency of electricity that's lost by transport. So those numbers vary according to distance in different parts of the country, but on average, about 30% of the fossil fuel energy that's put into the grid is lost just in inefficiencies in the grid. So there's a big move to make the grid smarter, more efficient. But the reality is, right now, it's not against using electric cars, just making the point that we've improved this quite dramatically. But I don't think we can rely on just one of these approaches. I think it has to be in all of the above. We need to be more efficient. We need to actually start looking at non-fossil fuel aspects of mobility, and we need to think about replacing the fuels used in mobility with something that can actually be quickly fueled and moved for transportation. So I'm going to end the lecture there today. When we come back after the exam review on Wednesday, we'll start talking about the actual process by which we get fossil fuels with coal, oil, and natural gas. Just to reiterate, exam review Wednesday, exam Friday. All of the lectures for the rest of the semester are now online, and all of the worksheets are available. The materials in the PowerPoints, as you know. So if anybody wants to get a head start, by all means, free to do so. But we'll get moving again on this on Wednesday. And last but not least, of course, is that all the lectures past next Wednesday will be, for the last week after we're gone, will be online on Wednesday before we leave for Thanksgiving, and available for you to watch at your convenience. And then it'll be a 3-day gap, a 3-day window to do the exam. Actually, more like 4 days for the exam. So hope everyone has a great start to their week. I look forward to seeing you on Wednesday.